So we were talking about crystal deformation last time, and today we are going to continue our discussion regarding the crustal deformation. Last time we discussed very important ideas. We discussed the deformation concept in general, and also we have idea about the fault and the joints. And we discussed the concept of the stress. And also we said that the stress, it could be confining pressure or it could be differential stress. And also we talked about the strain, and we discussed the elastic deformation and the brittle and the ductile deformation. And I hope the idea is clear for you. It's a very important concept. You are going to face that concept again and again as long as you are in the field of civil engineering. So if you understood the elastic, brittle, ductile deformation, the next courses is going to be easier for you. And we discussed also the factors that affecting the rock strength. We said that if the temperature increased, that means the rock tend to deform by ductile deformation, whereas cooler rocks tend to deform by brittle deformation. And also the effect of the confining pressure. If you have confining pressure, that means the rocks tend to undergo ductile deformation. And also we said that the rock type, also it has effect on the ductile or the brittle behavior, as well as the time. And we say that most rocks exhibit or show brittle behavior in the upper 10 kilometers of the crust. And as a result, you could have joints. This one just like fracture. And actually, they are going to be parallel to each other without any relative displacement. And we have the faults. We are going to have fracture like this one, but the fracture is going to be associated with relative displacement. Like you can see here, that part moved down relative to this part. And also we have the faults, which is like wave shapes deformation, look like waves. And mainly that because the rock is subjected to compressional stresses and the behavior is ductile. And here, this table is important for you to understand. We have the columns. Column number 1 represent the compressional stresses. Column number 2 represent the tensional stresses. And column number 3 represents the shear stresses. Row number 1 represent the brittle behavior. Row number 2 represent the ductile behavior. And as you can see, you are going to have different types or different type of deformation. Also, we discussed this last time. Today, we are going to talk about the faults and the joints and the fault in greater details. So we are going to start with the fault. Say that the fault, like you can see here, is going to form as a result of the compressional stresses. And we need to have ductile behavior. So when I press the layer of the rock, I'm going to have wave shape like deformation. So if we are going to talk about the characteristics of faults, we need to know that most faults result from compressional stresses. And because of that, we are going to have shortening and thickening of the crust. So we are going to have shortening, and the thickness of the crust is going to be increased. And there are some terms associated with the faults we need to understand. The first term is the hinge line. Because we are going to have waves like this one, that means we have bending. So we have axis through which the limb or the layers of the rock is going to bend about. So the limb here, it's rotating about an axis. We're going to call that axis hinge line. So in this case, that line here in that direction is the hinge line. It could be here, or it could be here, or it could be here. The most important point, the limb is going to rotate about that line. So here is the hinge line. And if I'm going to connect the hinge line, assume this one hinge number 1, 2, 3, 4. If I'm going to connect them together, I'm going to have a service, a plane service. And we are going to call it axial or axial plane. So we have hinge line, which is through which the limb is going to rotate, and we have the axial plane. It's the surface connect all the hinge line. And if you have fault like this one, if it's subjected to erosion condition, because that part is higher than the other parts here, this part is going to be eroded by the erosion means, which we discussed earlier in the previous lectures. So this figure here is before erosion, and that figure here is after the erosion. And we have features or types of the faults. If the fault is going to be like that in the wave shape, we are going to call the upfolded layer. Here we have upfolded layer, and here we have downfolded layer. The upfolded layer, we are going to call it anticlines. So anticlines refer to the upfolded rock layers, like this one. So in reality, we are going to have something like that. So this layer is upfolded. Also this one and that one. Synclines, on the other hand, is opposite to anticlines. This one, syncline, is downfolded rock layers. In reality, the layer, it will be like that, downfolded, like you can see here. So we could have upfolded rock layers and downfolded rock layers. We have anticlines and we have synclines. And that depends on their orientations. The anticlines and synclines can be described as symmetrical and asymmetrical. If it's symmetrical, that means if you are looking at the axial plane, if this one is the axial plane, which is connect all the hinge lines, this part is a mirror image for that part, which means, in other words, the limb on the left-hand side is identical to the limb on the right-hand side. If it's asymmetrical, that means the limbs on the left-hand side is not identical to the limb on the right-hand side. We call this asymmetrical fault, while this one is symmetrical fault. The asymmetrical also, it could be divided into two types. We have overturned and we have plunging. In the overturned case, we're going to have one or both limbs are tilted beyond vertical, like this one. If this one is a vertical one, we are going to have overturn. So this one is a special case for the asymmetrical fault. We are going to have turning beyond vertical. The last case, which is the plunging, which is like this one here, we are going to see that the hinge line or the axis of the fault penetrates the ground. So if you are looking here, if you are going to form a plane for that point here, so we are going to form a plane like this one, and assume here we draw horizontal line. So if you draw horizontal line, that means I have displacement between that line and that plane. It's going to equal that distance here. And if you have plunging anticlines, in that case, the axis of the fault is going to penetrate inside that plane. So if you draw angle here, we're going to call it plunge angle. This one is going to have a value, not 0. In other words, the hinge line for that case is going to penetrate the ground, which is this one. And if the erosion condition are presented, in that case, this part is going to be eroded. So we have anticlines, which are the upfolded rocks, this one. We have synclines, which is the downfolded rock. And the anticlines or the synclines, it could be symmetrical or it could be asymmetrical. And the asymmetrical, it has special conditions. We have the overturn and we have the plunging. The overturn, which means that one or both the limbs are turning beyond vertical. While in plunging, we are going to find that the axis of the fault penetrate the ground, like this case. And if we are going to have erosion, the figure is going to be like that. Any questions so far before we move on? Is it clear for you? You know, here we have, we put a lot of information here. Okay, be my guest.
Excuse me, Doctor. I didn't understand before erosion and after the erosion, the figure here. It looks like something
in front of me.
Yes, this after erosion, what happened to this sectional area of the Earth?
We know that when you have a higher plane here, like this one, the wind is going to be effective at that part more than that part, right?
Okay.
When a wind strike, which one is going to be affected more? That part here, of course, or that part?
The top. Of course, the top part.
So the top part is going to be subjected to the erosion conditions. So we are going to say that if erosion are presented, in that case, we are going to have something like that, because the part here and some of the part here is going to be eroded. And as a result, I'm going to have something like that.
Mhm.
Okay?
Doctor, the part in the middle, if the wind is taking the top, why did it take all of the top? The rest of the rest part, is it has a conditions, or it's just the natural?
Think of this one like if you are going to have a knife, or going to have
Okay.
a knife, then try to cut this one and try to see what will happen. Try to take a knife and take this part away. And try
Okay.
to look on the top side. You may going to visualize the erosion.
Mm-hmm.
But the main point is, if erosion take place, you are going to have some of them into other types of faults. Like you can see here, you have anticlines according to the layers here of the rock. We have anticlines, and here we have synclines. So here we have anticlines, and here we have synclines. Of course, if you have anticlines, the layers here is going to be the oldest strata. And on the sides, you are going to have the youngest strata. While in this case, where you have synclines, the layers in the middle is going to be youngest strata, while the one on the sides is going to be the oldest strata. Because the erosion is going to take the soil here, because this one is its position in the higher places. The erosion condition, we are going to take the soil here and put it there. So this one is going to be youngest, and this one is going to be oldest. So this one represents the oldest strata, and this one represents the youngest strata. And also, if you are going to have some conditions, erosion conditions, we are going to have dooms in case of anticlines. And in case of synclines, we are going to have basins. So we have the dooms, which are described by upwarded circular feature. We have circular feature here. And in the basins, also we have circular features, but this one is downward. Also is other type of the faults. The last one is monoclines. The monoclines is very large, and it look like step. So here the anticlines look like step, not like a wave. So if you have a large area and this one look like a step, and you have horizontal sedimentary strata like this one, we call this monoclines. And if this one is sedimentary strata, it means that that part is easily removed by the erosion. So if you are going to have fault, but the fault in the shape of a step, so this one look like a step, and that part is made from sedimentary rock or sedimentary strata, then the erosion is going to remove it. And as a result, we are going to have something like that. So this one, it look like a step, And because this part is sedimentary strata, is going to be removed by the erosion. And we are going to have something like this one, which is monocline. Any questions about the type of the faults? Okay, let's move on. And we need to talk about the faults. And I want you to focus, because if you missed a small part, you are going to miss the other parts. So please, I want you to focus here. We already defined the faults. We said that the faults are fractures. So if you have fractures, if this one is rock number A and this one is rock number B, and I have fracture between them, then I have a fault. But this one should be associated with displacement. So I need to have displacement between rock A and rock B. And that sudden movement or displacement are the cause of the most earthquakes. And next lecture, we are going to talk about the earthquake. So now we are going to have strong, solid background regarding the earthquake. So if you have a fault, the fault is going to be associated with displacement. And in order to describe the fault, we need to know the strike and the dip. We have many types of the fault, and all of them are described by the strike and the dip. So very important to understand what does it mean by strike and what does it mean by the dip. So this one is rock A and this one is rock B, and the fault is going to take place here and is going to be associated with displacement. The direction of the horizontal line on the inclined surface is, this is the inclined surface, and here we have the horizontal line. So we call this strike or line of the strike. And the dip is the angle of inclination. So the dip is the angle of inclination measured from the horizontal surface. So I have the strike, which is the horizontal line on the inclined surface. So if you draw a horizontal line on that inclined surface, we are going to call this strike. Whereas that angle here, the angle of inclination, which is measured from the horizontal surface, we are going to call it the dip angle. So we have the strike and we have the dip. We are going to describe all types of the faults by their strike or by their dip. So any questions about the strike and the dip before we move on to the next concept? It's very important to understand this, the strike and the dip. Okay. So the first type of the dip slip, the first type of the faults, we are going to call it dip slip. Slip means displacement. So in this type of the fault, we are going to have displacement associated with the dip. So this one is a dip, or we are going to call this dip direction. And in this case, we are going to have displacement in the direction of the dip. So this type here, it has been described by the dip, and we are going to call it dip slip. So this one is the faults occur when movement is parallel to the inclination or the dip. So here we have inclination we have the direction of the dip. We are going to have displacement or movement parallel to the dip. And again, we need to understand very crucial idea, which is the hanging wall and the foot wall. So assume you are sitting here and rock A and rock B was a 1 unit and you were sitting here. Then part B or part A separated from part B and you are sitting here and you are going or if you are planning to go to the surface of the rock A. In that case, you are going to hang yourself in order to get here. Then what if I want to go to the surface of the rock B? In that case, I'm going to use my feet in order to go there. The rock on the left-hand side, we are going to call it the hanging wall, because I need to hang something in order to get there. While the rock on the right-hand side, this one, I need to use my feet in order to get there. So I'm going to call this foot wall block. So this one is the foot wall block, and that one is the hanging wall block. And the hanging wall is the rock surface above the fault. So the rock surface here is above the fault, while the other one, the foot wall, the rock surface below the fault. So it's very important to differentiate between the hanging wall and the foot wall. And the dip slip, which is described by its dip, the direction of inclination, we have two general types of dip slip fault. We have the normal and we have the reverse. If it's normal, then the hanging wall moves down. The hanging wall is going to move down. If it's reversal, in that case, the hanging wall is going to move up. So again, if you are stuck here, you should be able to know which one is going to be the hanging wall and which one is going to be the foot wall block. If I'm sitting here, if I'm going to go to the surface of that rock here, I need to hang something, hang a rope in order to help me to get there. Whereas if I want to get to the surface of that rock, I need to use my feet. So this one is the foot wall block and this one is the hanging wall block. And here I have that case. I have dip slip. And I say that it could be normal or it could be reverse. If it's normal, that means the hanging wall is going to move down. If it's reverse, it means the hanging wall block is going to move up. So here we have the normal fault. So if I'm sitting here, so I need to hang something, it means this one is the hanging wall. If I'm here, I need to use my feet in order to get there. And this one, as a result, this one is the foot wall block. And here we have movement. So obviously, this one, the hanging wall, moves down. It means that I'm going to have a normal fault. And also the normal fault is associated with the tensional stresses. So the first condition for the normal fault, I need to have tensional stresses. And the other condition is the hanging wall is going to move down relative to the foot wall block. Yeah, we have real picture for that. As you can see here, that layer, it should be there, which means that I have relative movement of the hanging wall relative to the foot wall block. It means that in that figure, I'm witnessing normal fault. The other one, which is the reverse fault, instead of having tensional stresses, in that case, I'm going to have compressional stresses. And in that case, the hanging wall block is going to move up relative to the foot wall block. So this one is a normal fault, and this one is the reverse fault. In the normal fault, I'm going to have tensional stresses, and the hanging wall is going to move down. Here, I'm going to have compressional stresses, and the hanging wall block is going to move up. Like you can see here, this part and this part were 1 unit, but this one moved up relative to that one. So in this case, we are witnessing reverse fault. Any questions so far? I know that I put a lot of ideas, but I hope you understood the interaction between all of these ideas. Any questions so far?
Doctor, does the angle of the fault have any relationship between the type of the material and the type of stress? Does the type of the material will affect the angle of the fault?
No, it has nothing to do with that. It has nothing to do with the type of the material, unless you are talking about if it's ductile or if it's brittle. Of course, for all of these cases, the material, it should be ductile or brittle for the fault to take place. It should be brittle. Because if you remember, when we were discussing about the brittle behavior, we are going to have a sudden failure like this one. If the material was ductile, then I'm going to have folding or stretching. So if I'm going to have a fault, that means the material is brittle in the first place. So I need to have condition. First condition, in order to have a fault, the material should be brittle. If the material is not brittle, in that case, we are not going to have a fault. We are going to have a fold. Okay?
Clear, Doctor.
Any other questions here? Okay, let's move on. We have other type, which is a threat fault. This one is a special condition of the reverse fault. But in that case, the angle of inclination is small, shallow. Normally it's going to be less than 45 degrees. So the angle here should be less than 45 degrees. So if I'm going to have reverse fault, which means that I have compressional stresses, and the hang wall is going to move up relative to the foot wall block. But here we have a special condition. The angle of inclination is less than 45 degrees, or it's very, very shallow. In that case, we are going to call the fault thrust fault. Like you can see here, the angle of inclination is very small, and the hanging wall is moving up relative to the footwall block, and I have compressional stresses. So in that case, I'm going to call it thrust fault. Now we are going to move to different type of fault. This time we are going to describe the fault by their strike. Remember the strike. Here we said that in the beginning we are going to describe the fault by their strike or by their dip. Okay? The strike is the direction of the horizontal line on the inclined surface, this direction here. And the direction here, the direction of the dip. So the displacement, it could move in that direction or in that direction. The normal, the reverse, the thrusts, all of them were moving in that direction here. Now, if we are going to describe the fault by their strike, the displacement is going to move in that direction. So let's get back here. We're going to talk about the strike slip. Slip means displacement. Strike slip means I'm going to have displacement in the direction of the strike. So that case described by a fault in which the direction of the movement is mostly horizontal and parallel to the strike of the fault. So this one is the direction of the dip, and this one is the direction of the strike. And in case of strike slip fault, as you might have guessed it, the movement is going to be in the strike direction, not in the dip direction. So if I have that area here, this part is going to move in that direction, which is parallel to the strike direction. And this one is the real picture for that in San Andreas fault. I guess this one is in California. The last type of the fault is oblique slip fault. This one is very special because this one exhibit or show both cases. You are going to have displacement in the strike direction, and also are going to have displacement in the dip direction. So in the strike direction here, I'm going to have displacement, and in the dip direction here, I'm going to have displacement. And if that case is presented, we are going to call it oblique slip faults. So I need to have tensional stresses. I'm going to witness displacement in the strike direction. I'm going to witness displacement in the dip direction. So this one is very dangerous. And in the beginning, I said that the faults is associated with the earthquake. The sudden displacement along the fault can produce an earthquake. Some of the most destructive earthquakes occur along strike slip, displacement along the strike direction. And something like that took place in Haiti in 2010. And even larger earthquakes occur along low angle thrust fault. Or if the angle is very low, we are going to call this mega thrust fault. An earthquake like this one took place in Japan 2011 and in Samarta 2004. And if I do remember that, I think catastrophe take place there in Fukushima nuclear plant. And I think the city is still locked up today. So earthquake, it could be very dangerous. The last thing which I want to talk about is the joints. The joint is very simple. They are going to have fractures in the rock, but without displacement, not like the faults. And most joints appear in parallel groups, like this one. They are going to be parallels and in group, and of course without displacement. And it's one of the most common rock structures and produced when rocks in the outermost crust are deformed and experience brittle failure. So joints, very simple, you are going to have fractures, and it's going to be presented in the outermost crust, and the behavior should be brittle, and they are going to be parallel to each other. Now I'm done with the crustal deformation. If you are interested or you need more information, you can get back to the textbook. You are going to have more information about it. But for us, what we have presented here, it's enough for us. Any questions so far here about the joints or about the faults? Very informative lecture. It's very important for us to review this one and know the strike direction, the dip direction, the difference between hanging wall and foot wall, and then the types is going to be easy for you, because like I said, the faults are described by their strike and their dip. Okay, now I'll leave the floor for you to ask questions.